Let's think about this. In this problem we've been talking a lot about pressure. So what is pressure? Well, everyone will recall pressure is the force over an area. Now, what does it mean? Well, we take an area here, like a wall, and we take a little tool, like this, and drive this with a force F into this wall. This is my force F. When I do this, and I feel a reaction over this area here. This area. I call this my area A. So my pressure is going to be my force over my area. Nothing new. The interesting part now is that I only can measure this pressure in this area here. And I can only measure it into this direction. So the pressure is a scalar for my force as a vector over an area. So for ourselves we can say the pressure we apply to the surface of the earth is our weight as the force over the area of our shoes. Now, if we walk in snow, the snow cannot withstand the pressure we sink in. The solution to this problem is that we increase the area of our shoes using snow shoes or skis, and this way we reduce the pressure and the snow withstands the pressure. Another application is driving a nail into a timber. Again, the pressure we can apply to the timber is the force with which we can drive the nail over its area. Now we want to have a high pressure because we want to drive the nail hard into the timber. What we do is we decrease the area. Actually we have quite a pointy end of the nail, and consequences that the pressure goes up and the timber cannot withstand that pressure. We move away from the solid to the liquids and the gases, and that's what this gentleman on the right did in the 1600s. Mr. Blaise Pascal did this in Paris. He took a balloon, as we can take an air balloon and fill it with a liquid, or in aerodynamics we treat air as a liquid to a certain extent, and apply through this piston here a force to this installation, F. Then over this area of this piston we produce a pressure, and again the pressure equals my force over my area. Now the interesting part, that is what Mr. Pascal found out, is that the pressure is now in this liquid, and it doesn't only exist into this one direction, but it exists into all directions, and we can measure it perpendicular to the surface of the walls. But it's not only there on the walls, it's everywhere in the liquid, and it's everywhere equal. So the pressure in these liquids is constant. That's the principle of Pascal. Now if you apply this principle, life becomes interesting. I have this little box here, which is connected to a pipe. I fill this box with a liquid which is supposed to be incompressible. That would be, for instance, water again. Could be cooking oil. Could be air, as long as we agree that it is not compressible. And of course I fill it up here all the way to the cylinder up there. Alright? I apply a force towards this cylinder again. My force F1. And the cylinder has a surface area of A1. Now obviously my pressure is going to be F1 over A1. Now I know the pressure exists in all directions in my little box down there, so I can choose an area A2, which quite handily comes in here, defined by the height of this device and its depth. So my pressure is constant. It is now my force 2, which will apply perpendicular to this surface, over the area A2, and I can write this, and I simplify now using black, F2 over depth times height. Force in Newton, depth meter, height meter, square meter, Newton over square meter is the pressure. Now I can use another one. I can use that surface here, and I will have a force 3. Force 3 pushes against this surface, which is L length and H height. So my pressure remains constant, and I can say my force 3 over an area 3, which in this particular case is length times height. Since pressure is constant, I can conclude that my force 2 over distance times height, area 2, equals force 3 over length times height. Or just a bit more simpler, force 2 over area 2 equals force 3 over area 3. That means I have a big area, I have a big force. I have a small area, I have a small force. Quite interesting, not very intuitive. I can ask myself, what force would I expect to be there? So I form this very long pipe, give it a surface area down here, and fill it up with water. And it is easily understood that this water has a weight. Weight is a force, and this force will press against the surface area equal to the cross section of this pipe. Aha! Now, let's keep it red. Weight equals mass times gravitational acceleration, right? We also know our water in this instance has a density rho, mass over volume. We measure this one in kilograms over meter cubic. Or mass, which I don't know at the moment, equals rho, which I can look up. Water is 1 kilogram per cubic meter, times volume. Aha, now I know my gravitational acceleration above around 10 meters per square seconds. I know my mass by having its density and volume. Aha, I need to find out the volume. What is my volume of this pipe? Well, it's relatively simple. It's this surface area here multiplied with the height of this installation. So I can replace here mass equals rho times volume stands A times H, surface area times height. Okay, I go back to my weight, would be mass rho A H times gravitational acceleration. Let's quickly check if this is okay. Rho is kilogram over meter cubic times in area, meter square, times in height, meter, times meter over square second, which is an acceleration. And we're supposed to have a weight, a force, which is Newton. So this meter times square meter is meter cube. I have kilogram meter over square second. That is Newton. Good. Now here's something very interesting. I can now calculate the pressure. You remember, pressure is force over area. My force is my weight, rho, the surface area of the cross-section of the pipe, the height of the pipe, and the gravitational acceleration, the whole thing over the area, which again is the cross-section of the pipe. I cancel out area and area, and my result is that my pressure is rho hg. Now again, let's make double sure that this is correct. That means kilogram over cubic meter for the density times meter over square second for the acceleration. Kilogram meter over square second we have here. This one we get out, square meter. Kilogram meter square second is Newton over meter square. That is the pressure. Now this is very interesting. We look a bit closer into this, and our pressure caused by the water column above is only influenced by the height and by the density of the liquid. Gravitational acceleration is more or less constant. Now when we look into this, we can find a design like this one. We have the pressure inside here, and we know it goes into all directions, all the same magnitude. And now I can define here my height h. Okay. I change my design a bit by mounting up here a big tank. And I fill it up to the same height h with water. What will happen? Well, intuitively we would say the weight increases because we have so much more water up there, and therefore the pressure in the balloon would also increase. But this is not the case, because our pressure is rho, we did not change this one, 1 kilogram per cubic meter. H, we did not change that one, it's the same. G, 10 meters per square second, we didn't change that one. So no matter how big the water tank is above our vessel, the only influence on our pressure is the height of the water column or the water tank. This is not very intuitive, it's quite remarkable, and we will use it in the next tutorial.